Hello everyone, and thank you for attending today's webinar, Using EBSD to Investigate Steel Microstructures. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck is available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of your slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier or via the EDAX website. Now I'd like to introduce the presenter for today's webinar. Matt Nell is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechSem Labs, known as TSL, upon graduation from the University of Utah in 1995 with a degree in material science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Now over to Matt.
Thanks, Jonathan, for that introduction, and welcome everyone to this webinar. The title is Using EBSD to Investigate Steel Microstructures. And just to kind of give an idea of what I wanted to try to accomplish with this, I wanted to show a range of steel applications and show how EBSD can be used to measure the microstructures from these different applications. And from that, show off some of the capabilities and features available in our software package, austenite, to better visualize, and I term it quantify, these microstructures. We can numerically characterize as well as just create a pretty picture of these. And with this, I'm kind of focusing on a wider range of applications, not really a lot of in-depth, but in a lot of these, there's more supplemental information available. I've kind of made notes on some of the slides where that's possible. So if you look on the EDAX website, you can find things on, say, retained austenite and things that we have a little bit more things in detail. Going into this, I've assumed a basic understanding of EBSD. I haven't included the standard, 5 to 6 slides kind of introducing the technique of what we're trying to do. So I'm assuming that that's something we can build off of. So, of course, I'd really like to start by acknowledging a number of people who've contributed to this, the data on this, Stuart Wright, Renee DeClo, and Will Lenthy at EDAX, John Carpenter, who was at EDAX a few years ago, Suzuki-san from TSL Solutions in Japan, Josh Kasher, Tim Ruggles, who helped on some HR EBSD work, Tom Voisin from Lawrence Livermore on some additive manufacturing samples, George Vandervoort for some nitrided steel samples, Tracy Nelson from BYU for some friction stir weld results, and Ryan DeHaa from Oak Ridge. And of course, this list is not comprehensive. As Jonathan said, I've been doing this for a lot longer than I like to actually count now. And I've had conversations with people in the steel industry, using EBSD, using OIM, and talking about their different applications and bring a lot of that to kind of putting this together. So why steel? Why did we pick this? It's the most important engineering construction material in the world. And this comes from theworldsteel.org, these values that we'll go through. But when I've looked at it, I do a lot of work trying to see where EBSD is being used via publications. you know, somewhere between, what do we say there, 57 and 65% of the papers published last year looking at either Science Direct or Google Scholar involve steel, at least as a keyword. So it's a lot of applications. There's a wide range of applications of microstructures. And the fact that I found really interesting was that it quoted 75% of modern steels have been developed in the past 20 years. And if the Eiffel Tower were rebuilt today, it would need 1/3 of the steel that was originally used. And I've looked a lot of you know, this light weighting of materials for, say, automotive applications, where, you know, there's always a push to say, can we use aluminum? Can we use magnesium? And it always seems like that as new other materials are introduced or talked about, you know, the steel industry pulls open a drawer and says, wait, we have another idea where we can push the performance of steel beyond what it is now. And the example I liked was something we saw just for a new car. So when I was a kid, my dad had a Bronco, so I always liked the Bronco. And this is the new 2021 Ford Bronco using a Generation 3 steel from ArcelorMittal, where it's 35% thinner with the same strength and using about 2/3 high-strength steel compared to traditionally around 50%. And the quote from this article, this is from thedrive.com, it says, evidently there are still ways to make better steel. I think that those stats from the earlier page shows that developing new higher performance steel is really a strong application. We really see a lot of use of EBSD in those sort of efforts. So to start, I wanted to talk about some friction stir welding and show some examples from a steel sample. If you're not familiar with friction stir welding, it's a solid state welding technique. It's of interest of steels because it works with dissimilar metals, can be used to weld steel to aluminum, and the mechanical properties come out better compared to other alternative welding techniques. There are different microstructural regions, and they make really pretty pictures for EBSD, as you'll see. And you can kind of see a little diagram here of how this goes, but again, the tool is pushed into the metal that's being joined. It stirs around, and the friction and the heat there, it describes it. It's a little hard to read the text on here, but it creates a doughy type structure. So it mixes things without melting. It's a solid state technique. And so this is from Car and Driver magazine that covered friction stir welding a few years ago. So this is an example from a friction stir weld. This is a stainless steel alloy. This is using what we call a montage scan. So it's covering a large area, 31 millimeters by 7 millimeters. And basically we take a field of view, we collect the data, we move the stage, we take another field of view, we repeat that, and when we're done, we stitch them all together to kind of see the microstructure. So this is looking at an area with a 10 micron step size. The map I'm showing here is what we call an orientation map. This is where the colors correspond to the orientation, in this case coming out of the surface normal direction. That will be the standard direction we use in the presentation unless I note otherwise. And we have the little colored stereographic triangle that shows how the colors correspond to orientation. So if it's red, it's an 001 cube face orientation for the cubic faces in steel. If it's blue, it's a 111. And so we see the weld nugget there in the bottom center. You see a little bit on the top where it's transitioned, and you see the base metal to both sides. If we zoom up along the interface in there, this shows what we call our image quality map. Image quality is a measure we get from measuring the average intensity of the detected diffraction peaks in the Huff transform. We measure that value, and then we map the variation as a grayscale image, and we see different contrasts. And we can see an example of this from a different steel. This is a partially recrystallized steel. IQ map contrast can come from phase contrast. That will just be difference in scattering from atomic number. It can come from you know, the generic term is strain, but as we deform the lattice, the diffraction is not as sharp, so the peaks are not as bright. Crystallographic orientation, some orientations will have more lines or more poles in it, so we'll end up brighter in the Huff transform. Topography and grain boundaries. As we come closer to grain boundaries, the patterns can start to overlap and the overall intensity decreases. So this slide just shows an example of a recrystallized pattern and a deformed pattern. You can see the sharpness difference. You can kind of see the intensity difference, but if we map that out on a grayscale on a map, you can clearly see the crystallized grains are bright and equiaxed. The deformed grains are much darker and more elongated in the microstructure. This is the orientation map of the transition region of that weld. So we can see on the top left kind of the transition zone and the base microstructure. A lot more polygonal grains with some twin boundaries in there. On the bottom right, we see the weld, where we see much more elongated grain shape, and we'll investigate that a little bit further. But we can get quite a bit of detail with EBSD of that, and this is a single field scan of about 1 centimeter squared with a 1 micron step size. Once we have those orientations, what we do with EBSD and with OIM is we typically calculate grains. And when we talk about grains, we define a grain in terms of a tolerance angle and a minimum number of pixels. So if we have our measurement grid, and we typically measure things on a hexagonal grid, this puts more of a packing factor of measurement points on a specific area. And each neighbor has 6 equidistant neighbors. So we can sample more neighbors of the same distance for local kernel measurements. We'll talk about that when we talk about some of those metrics. So we start with our first point that has some orientation. The orientation is shown by a little unit cell, and we've colored it red. We check the next pixel. If the misorientation between that pixel is less than our tolerance, then we say it's within the same grain. And we repeat this process. We check this one. It's still within the same grain. And we check this one. It is not within the same grain. And I just want to point out here, between these first 2 pixels, our default tolerance angle is 5 degrees. So if the misorientation here was, we'll say 4 degrees to keep it round, and between the first and second pixel is 4 degrees, and if the misorientation between the second and third pixel is 4 degrees, the misorientation between the first and third is then, of course, 8 degrees. So, you can get a lot of grain orientation spread within a particular grain, even if the misorientations between points are lower. And we'll see some examples of that a little bit later. And if we repeat the process, it checks and groups things in to say, what's the boundary of the determined grain? And once it's found, it then colors everything here. And then we go to the next spots and we repeat the process. And we start to fill them in to determine where the grains are determined. And you can see in this particular example, there's one grain that has 1 pixel, there's one grain that has 2 pixels. We can do some filtering by the minimum number of pixels. And that's important just because how this falls into place depends on your microstructure, but also on your sampling size. As you go to smaller and smaller step sizes, you're able to resolve finer and finer grains, and so being able to adjust that if you go to coarser step sizes, may require a different threshold. Once we've determined the grains, we can then randomly color that. We call this a unique grain color map, or just a grain map. The colors are such that no 2 adjacent grains have the same color, so it really shows morphology, the size and shape of the grains. And again, we can see that the weld grains are a much different shape than the base metal. And of course, if we know what the grains are in terms of pixels, we can figure out a grain size distribution. That's shown here. We can define this grain size distribution a number of ways. I think the default often that people think about is in terms of diameter. That's an easy one to get out. That's the default, is to show diameter. But of course, as we look at some of these grains and grain shapes, diameter doesn't always make sense when they're non-equiaxed grains. So we can do grain area, we can do ASTM numbers, we can do intercept length. There's a number of different ways of representing grain size that can be applied to the particular microstructure. And then we can do some fun things to try to link these things. So this is something we call interactive analysis. So I've just gone into that histogram on the left, the grain size histogram, and I've drawn over a color scale. So the smallest grains are blue, the mid-range grains are more of the yellow-orange, and the largest grains are red. And once those colors are applied to the histogram, they can also be applied to the map. So we see that there, and we can see that sure enough, the weld grains are larger, they're red. The base metal is more in the middle range. The small grains are there, blue, but there's just fewer of them and they're smaller, so they're harder to see. The other thing I'd like to point out with this to remember, with EBSD, we have the choice of including or excluding the edge grains. You know, these grains that we see that are touching the edge, we're not measuring the full grain. So mathematically, you probably don't want to include them from your distribution. But from a map, it makes it look better to color to the edges. It looks a little weird if you throw them out. So that's why I've shown them this way. But if I'm trying to extract it correctly, I generally will exclude those. And I highlight the coloring scheme. This is when I make my typical joke that I'm colorblind. And Stuart Wright, one of our programmers, has decided to make the first two colors in a lot of our color palettes red and green, I think because I beat him in golf once. But we have the ability to customize and adapt coloring schemes depending on what we want to show. And I'll show some examples of this. But this just shows the coloring gradient tool in OM analysis. So we have different numbers of colors. We can do, you know, 1 color, 2 color, 3 colors. This is a 5 color default. And so again, it kind of is that default blue, yellow, red range, but we can come in and adjust the different colors along different points of that profile. We can move where they lie. You can really get this to match what you want to show depending on the type of distribution you're looking at. There's a number of presets that are available. You can load and save them. And there are some other ones that are this uniform color mapping options I show on the right there. There is even a colorblind option now that allows you to really represent the data with higher fidelity. So this is now selecting colors more specifically. This, I thought, highlighted the different ranges a little bit easier to see. So I made the smaller grains yellow, the middle range ones blue, and the larger grains red. You can kind of see how those fall into place with the map there. So you can customize how you're coloring things to really showcase what you want to see. And once you've done this, you know, we've done this highlighting, we can create what we call partitions or subsets of data. So in this case, I've taken just the middle region and said, everything that falls into this, let's take that as a subset of data, and then we can do our own analysis. So I could look at, say, the grain size of the texture just from that data. We could also take anything that was not highlighted and create another partition to compare those really easily. And so as we talk about some of our phase analysis, there are times we do stuff like that, and I'll talk about that in a few slides. One of the things EBSD really excels at measuring are grain boundaries and what I've called here the location and character of grain boundaries. And what that means is we can tell what the misorientation between 2 pixels are. You know, we measure that angle. We use that when we created the grain tolerance angle. So if it's a misorientation that's between, say, 20 and 25 degrees, we can color it one value. If it's between 40 and 50 degrees, we can color it another value. And so we can measure lots of grain boundaries with EBSD. It's really the most efficient tool for looking at this orientation information because we can look at a large area with fine spatial resolution. And so here we've used a color scheme across the entire misorientation distribution. We see where they show up in the map. We can also measure local misorientations, and it's a little tricky how we choose to describe this. You know, sometimes it's termed strain. It's really not strain, but that's what it's called, or plastic strain. But essentially, as we permanently deform a material, it introduces misorientations. And if these misorientations are large enough to be detected with EBSD, we can count them. And so, you know, typically for regular EBSD, our precision is somewhere around 1/10 of a degree. And so when misorientations are higher than that, we can start looking at how those are distributed. And so we do this in one term of a map called a kernel average misorientation map, or a KAM map, where for every pixel in the map, we look at the misorientation between its 6 adjacent neighbors, and we take the average of that and color it accordingly. So the color scale used here, blue is basically, you know, a 0 misorientation. Red would be essentially 5 degrees, and we use 5 as often as a cutoff. From after 5, it starts to be more of a higher angle, maybe a grain boundary. And so we can see in this map, you know, the weld area sort of has a higher KAM value. It's a little brighter in the top right than on the base metal to the left, but there's still a good deal of KAM strength kind of throughout the microstructure. And we'll show some other examples of how we can count these misorientations. We'll also show some examples of going to higher precision with HR EBSD. Now, I started off with this very large data set to get an idea of a large scale of data. Once we have that data, we can also do cropping. So I've just come in here and said, show me a region of the base metal. It gives us an area. In this case, it's just a rectangle we've pulled out. Once we have that, we can do what we call texture analysis. Texture analysis is just looking at the orientation distribution of the measured orientation. So it fits a function that describes the distribution. From that, we can get an idea of what we call the strength of a preferred orientation. And I'm sorry, as I look at this, I realize I didn't put the color scale, but essentially, you know, these colors on the pole figures, so these images on the right are what are called pole figures, which show the spatial projection of the orientations onto the sample reference frame. So the center of the pole figures show the sample normal direction. The A1 shows the top to bottom direction. So A1 is the top of the map. A2 is the left-hand side of the map. So if you use your right-hand rule, you'll see how that kind of aligns with that map. So what this shows us, if we look at the 111 pole figure, is there's sort of a strong peak in the center of the 111. It's a little bit offset, kind of coming out the center of the sample. That's why when we look at that region, there's a good amount of blue. And if we had the scale bar, we'd be able to tell how strong, how much over random is that distribution. And we can see it's sort of annular around that. It's sort of what we'd call generally a fiber texture, at least close to a fiber texture. It's got some funny shapes to it. But we can see it's more randomly distributed around the clock face of that 111. So that's what texture can show us. I can also come in and crop. I did my best to crop the weld nugget, so it wasn't a rectangle. It's what we call a polygonal crop. Trying to crop out those weld nugget grains. Looking at the texture of these and see it's quite different. There's more of a 001 alignment along the A1 axis. And just to kind of investigate that a little bit more, I went and pulled out the grains of just the weld nugget. So from this crop data, I specified, showed me all the grains that are larger than 20 pixels. So here's a grain map showing that. So we see a lot of those elongated grains. Once I have those grains identified, I then fit an ellipse to each grain. So here we fit an ellipse, we determine a major axis and a minor axis. We determine an angle between the horizontal and the major axis. And I've just shown those ellipses in white to kind of show how they fit those elongated grains. So when we're looking at grains, we can get an idea of their shape and shape distribution. But from this, what I'm now doing is, if we look, we can see where the major axes are. I'm showing what crystal orientation is aligned with the major axis. And we can see that most of these, or at least a good number of these, are trending towards the red direction. That kind of gives us an idea if some of that grows preferentially as the grains grow in that direction. And we can see, you know, there are a number of grains kind of aligned top to bottom in that A1 axis, which is explain that orientation distribution in the pole figures. So I want to jump to the next application, which is additive manufacturing. I hazard a guess that if you're listening to this webinar, you've heard about additive manufacturing. It's certainly a pretty strong buzzword market of interest that's receiving a lot of attention on a lot of fronts. But additive manufacturing is basically a process where we build up parts, where instead of removing parts, we're adding parts to create a shape. So this is just an example. This is from Malvern Panalytical, where you have a bed of powdered material. We hit the powder, in this case with a laser, but both lasers and electron beams can be used. It fuses the powder particles together. It solidifies those, and so we can use the laser to raster out the area we're interested in. Once the layer is complete, we drop the build platform down. We reset the powder on top, and we do another layer. And so we can build, you know, complex shapes generally pretty easily with additive manufacturing. And so this is just an example. This is using laser powder bed fusion. This is a 316L stainless sample. This shows the orientation map. Again, this is a large-scale montage map, but it's showing what's termed the horizontal build direction. In that case, what it means is that the layers are building up towards us. So we're looking at the very top layer after the fabrication. And you can kind of see there, these are kind of the greenish colors. I hope they're green. This is where my color blindness will hurt me, but they're, to me, a greener color. Whereas if I compare that to what's now termed the vertical build direction, this is where the build plane passed left to right, not out of the plane of the surface for this particular sample. So if we look at those, you can see the shape of these two samples is essentially the same, but they were built in two different directions. And that's just important because, you know, if you were to look at a part and if they look the same, you know, you wouldn't realize that, hey, the mechanical properties are actually defined by the microstructure. And if the microstructure is different from one to the other relative to the shape of the part and the directionality of an applied load, you can get very different performance. And that, I think, sparks some of the interest in understanding the microstructure of these 3D printed parts. So looking at these in a little bit higher magnification, you can see that the microstructure is very different between the horizontal and vertical directions. And this is just essentially parts of how the energy beam interacts with the particles, the solidification and heat transfer rates going through things, and then how it goes from one layer to the other, the direction of the rasters, and there's a lot of things going on in there. And you know, again, if you're able to adjust your build parameters to adjust your microstructure, and microstructure determines properties, being able to measure your microstructure is a key component in really moving forward with this. And this is just a really good example. This is from Oak Ridge National Lab a few years ago. This is in electron beam melting. This is actually a nickel superalloy, but they varied the build conditions to actually write DOE into the microstructure. And I just think it's a really cool example of the idea of controlling localized properties in additive manufacturing, which, you know, I don't think you could do as easily through more traditional means of fabrication. And this just shows the grain maps of those horizontal and vertical directions. Again, randomly colored grains. And you can see that the grain shapes are very, you know, non-orthodox. They're not your nice equiaxed grains. And so if you find this interesting and want to learn more, I will give a plug to Dave Roenhorst from the Naval Research Laboratory. He has done a lot of work in looking at these microstructures in 3 dimensions with EBSD. So the image on the top left there is his system where he has his SEM coupled with a robot going over to an automated polishing system. So the robot will polish the RoboMet will polish the sample. It automatically transfers to the SEM. It does the EBSD and then repeats the process for serial sectioning. And he's looked at these grains in 3 dimensions, and they're very interesting looking. And so Dave is giving a webinar with us in about a month. So if you're interested in this, I'd highly recommend it. It's very interesting. In my work, I was looking, or starting to look, it's still in progress, but looking at these, at more the structure at higher spatial resolutions. So here we're looking at an area where we can see within some of the grains, we see that the color changes. There's small changes within a primary color. And that represents small changes in the misorientation. And so if I look at this in terms of a misorientation profile, so you can see on the left, I've drawn a line sort of from the bottom to the top within that single grain. I've overlaid on there unit cells along that profile line. You can see that along the line there are small changes in orientation. And we can see that on the profile on the right, the misorientation profile. The right line shows the point-to-point misorientation. So from point to point, the misorientation is not changing a lot. But if we look from the bottom to the top, there's sort of a cumulative effect of how that misorientation has developed throughout that grain. There's some structure to that misorientation. And we can visualize that with other types of maps. One is what we call a GROD, or Grain Reference Orientation Deviation map. So in this case, what we do is we calculate a grain, like we showed earlier. We calculate or we determine a reference orientation There's a number of ways we can do that. And then once we have that reference, we can shade each point within the grain as far as misorientation from that reference. And you can see as we do that, I've drawn the black lines on there are the determined grain boundaries. So it gives us some idea where the grains are located. Within the grains, you can start to see, we see this kind of a cell subgrain structure, kind of as a fingerprint of the deformation. And so we can compare this to TEM results. So this is a bright field TEM image on the left, and you can see that cell structure pretty clearly. On the right, you'll see this is the image quality map from one of those higher magnification images. You can see we actually can detect some of that cell structure in the bottom just through the image quality as well, which I thought was really interesting. And we can look at this with what we call HR, high angular resolution EBSD. And so this is a technique that provides higher precision in the orientation data. And this is achieved by comparing two EBSD patterns in a cross-correlation Fourier space, looking for just small shifts of features within the pattern. This is in contrast to our standard Huff-based indexing. And so this is data that was collected with our Clarity direct detector to get really high quality patterns, looking to see how well we could measure this. And from this, you can see the orientation map. You can see there's some slight color changes in this top grain here as far as variations. And when we do this HR CAM map, you can see how we start to very clearly resolve where some of those cell walls are present. This can then be used to measure the GND, or geometrically necessary dislocation density. So this is a measurement that's basically, depending on what the misorientation is, there's a certain amount of dislocations that are necessary to create that angular change. And so it says it's the curl of the orientation field that's used to do that calculation. So we can figure out where the GNDs are present to kind of visualize those. And once we have that, we're also able to kind of look at the stress and strain that comes out of that cross-correlation analysis. So this just shows along that a profile line horizontally going across some of those cell walls, and we can see the stress state going along that. So we see where it can kind of go from a state of compression to tension along those different parts of the dislocation structure. And so that's I want to say it's relatively new, but it's been around for a while now, of more information we can extract from the EBSD patterns. The next example I want to talk about is TWIP steel, or twinning induced plasticity steel. You're probably familiar with sort of this curve here. This is a curve of strength versus elongation or ductility, kind of this banana-shaped curve. And a lot of work going to push the properties to try to enhance both strength and elongation. You want materials that can do both. So this is just a little diagram from World Auto Steel. And for TWIP steels, deformation twinning and being able to measure that and understand that, deformation twinning is what's used to kind of achieve these superior mechanical properties. So this is just, again, an image quality map of a TWIP steel. You can see the twins come out as those parallel linear features within the microstructure. We can see the orientation map there on the right. You can see the deformation in that orientation map. It's those variations of colors. I think they're really pretty just in terms of variation, but you can see it a lot in this bottom right one where we are in the triangle kind of transitions from blue to greens. There's a lot of misorientation and twin boundaries present in these microstructures. We can measure this with more detail in terms of what we call grain boundary analysis. So the distribution on the left here shows the misorientation angle distribution. So this is just showing the angle between orientations. You'll see there's a strong peak there at 60 degrees. That corresponds to our twins in the material, and we'll characterize that a little bit further because in addition to angle, we can also determine the axis of rotation. And the twin boundaries are the primary twins are 60 degrees, about a 111 axis. And we can also see we can do some analysis there on the right where we look at what we call the correlated misorientations. That's look at the misorientations point to point. We can look at the uncorrelated. This is where we kind of compare one point to every other point. And then we can look at what a random distribution would look like. So this just kind of gives us an idea of how the spatial distribution of those orientations influences the grain boundary character distribution. And again, like we did previously, we can highlight these. So with color highlighting, we see the twin boundaries come out in red, sort of as we'd expect. And we can characterize all the boundaries in there. So the plot here on the left shows our GBCD, where we have low angle boundaries, CSL boundaries, and high angle boundaries, and we can kind of get an idea of which is which. The distribution on the right characterizes CSL boundaries by what's termed sigma values. CSLs are a boundary model, kind of showing the frequency of shared lattice spaces between two different lattices for adjacent grains. And so we get an idea that in this case there's a high fraction of sigma 3 boundaries. Sigma 3 corresponds to those 111 60-degree rotations. But we can also see there's a small little peak at 9, which would be a twin of a twin boundary. And so we get a lot of information about grain boundary character with EBSD. And this can be important for something like stress corrosion cracking. This is in a pipeline steel. This is just an example of a crack going through a piece of this steel. The cracks tend to propagate along specific grain boundary types. They generally try to avoid going through a twin boundary. And so there's work done that's called grain boundary engineering, where materials will be subjected to different deformation and heat treating cycles to improve the number of twin boundaries to help enhance the corrosion resistance. I want to talk a little bit about looking at different phases of steel different phases in steel. Generally it's a lot easy to think of steel as think of it as, a single or dual phase steel. Oftentimes there's lots of other stuff going on in there. So I was talking about pipeline steel. This is a 2205 duplex steel used with good corrosion resistance and mechanical properties. But if it has a sigma phase, it can be detrimental to this performance. So when they heat treat the sample and weld the sample, they try to control the conditions to avoid precipitation of the sigma phase. And so these are two different examples of the 2205 that were heat treated a couple of different ways to measure the amount of sigma that was present. So we can see, on the left, the sigma is shown in blue. Sorry, these are not the same color scale. The sigma is on the yellow on the right, and you can see, the different amounts that are present. And in this case, these three phases are crystallographically different. And what I mean by that, if we think austenite, one of the phases in steel and iron is face-centered cubic, or FCC. Ferrite is body-centered cubic, or BCC. They're very distinct crystallographically. So what that means is that the projection, the planes that diffract are different. The projection of those planes onto the EBSD detector are different. For EBSD, for our Huff-based indexing, we're measuring the angles between these planes. So if different planes are diffracting, angles are different. It's very easy to tell these different phases apart. When structures start to become more crystallographically similar, that's when EDS can supplement EBSD. And you can just see for this example, this is the 2205, and I've created just a single EDS map where it's RGB colored. So red is iron, green is nickel, blue is molybdenum, and you can see where the sigma phase is by highlighting where the moly is higher. And we see a strong correlation. If we looked at the phase map next to each other, they correlate well. And so it's very easy to collect simultaneous EDS, EBSD data now in a modern EBSD system. Both the EBSD and EDS detectors and the SEM chambers are all designed with that in mind. This is just an example of looking at different carbides in steel. So on the left here, these are looking at different MC, carbides, where M is chromium in this case. So we're looking at a 7-3 carbide and a 23, I wish I had my glasses on, carbide, the blue one. And you can see how they're distributed. They have a very interesting structure. Some of the carbides have sort of an interior-exterior carbide distribution. On the right, this is looking at tungsten carbide, vanadium carbide in a ferritic matrix. We can see where they're present. So, you know, carbides, we can resolve those out nicely, but sometimes it's not always as easy. So this is just an example from cementite. The image on the left, kind of larger globular cementite, those come out nicely. On the right here, this shows more of a perlitic microstructure, where the bands of iron carbide is much finer, it's much smaller, so it can be more difficult to detect, especially with larger step sizes. And there's been work that's been done that shows, you know, if you go to lower voltages, you can start to resolve that better. So you can get it, but sometimes it gets to be tricky, sometimes from a physics point of view, sometimes from a sampling point of view. And then this is one, we were saying we didn't have a question that came in before the webinar started to talk about this a little bit. This is a question that's been around for EBSD for a long time, of how do we differentiate something like martensite from ferrite? So martensite is body-centered tetragonal, and it's a slightly distorted BCC lattice, and you know it's distorted from the temperature change and phase transition from austenite ferrite into martensite, of how that strain is retained into the unit cell. And so basically what it means is that that cube is just slightly changed. And one of the things that's tricky is the slightly can depend on a lot of things. It's not always uniform in your alloy. Can vary with kind of local carbon content. And so the interplanar angles between these phases are very similar. It can be more difficult to differentiate. And this just shows an example of this. So there's our ferrite martensite patterns again, but on the image there for the martensite pattern on the right, the C image, it shows the white martensitic overlay and the black ferritic overlay onto the same pattern. And you can see it places the white and black lines are essentially lined up, and the shifts between them are very small. So they're very subtle shifts between the two. So it's difficult for the Huff to reliably differentiate. It can always differentiate, but it's not always 100%. And so traditionally, there have been a couple of approaches, and one that comes from about 20 years ago from Alan Wilson and George Spanos at NRL was looking at the image quality difference between the martensite and ferrite. So this is kind of one that's been used quite a bit. You can see there's kind of a bimodal microstructure. You can figure out where you want to draw a line. So this is an example with our velocity CMOS camera, where you can clearly see the difference between the ferrite and the martensite, both by image quality, how bright the grains are, but also sort of the shape of the grains. And this is used to show up because it is an easy example. As we get into some complex microstructures, trip steels and things, you start to throw, bainite and things into this. It's not always this easy to see. I don't want to set expectations that this is an easy problem, and there's been a lot of work going into this. And people are using machine learning to try to characterize the different distributions. But this is just an example showing how image quality can change. We can color the image quality this way to show it. And we can also see it again with local misorientation. So the martensite generally will have a little bit more misorientation. So if I put my cam map here and we compare that to the distribution here, you can see there's pretty good correlation between image quality differentiation and cam distribution. And of course, we're working on other ways of trying to differentiate that as well. And I think we'll have at least a talk at M&M about this this summer. This is just an example from a nitrided steel. So nitrogen is used to create a surface layer to create a layer of higher hardness, improves wear resistance. This is just an SEM backscattered image of that structure. And so to characterize this with EBSD, first thing I looked at is what we call a Prius image. The Prius uses different regions of our detector to create different contrast mechanism images. So you can see on the left, we're getting atomic number contrast. In the middle, we get more orientation contrast. On the right, we get more of a topographical contrast. That's, again, just selecting from the top, center, and bottom of your EBSD detector to monitor the signal in those regions to create those images. So we get some nice just pictures of the microstructure with Prius. If we look at the phases, we see here there's the ferritic phase in red. There's the blue and yellow phases are a couple of the nitride phases, and then there's a moly sulfide phase as well. But it has some trouble differentiating these. There's some speckling within the base ferritic grains. So with that, we use what's called simultaneous EDS collection for chi-scan or chemical indexing scanning. So this is just that same RGB EDS map where we can see the nitrogen in red, and you can kind of see, it's a little hard to see, but you can see the shading of where the nitrogen is present. We can see where the, I put manganese, I don't know if it's the manganese for the manganese sulfide. And then we can use that to select the correct phase for each point based on the chemistry. From that, we can differentiate better the crystallographically similar phases. We can see the true phase distribution, and then we can also start to see how the nitride phases are present on the outer layer, as well as how they're penetrating into the microstructure through the ferritic packet boundaries. And so we can see that in terms of the comparison before and after chi-scan. I think this just shows very nicely why using both together is very nice. It's a very easy way of better resolving the phase information correctly. We get a better overall picture, and there's really no penalty for having both. And then we can look at the orientation information. And so this just shows the orientations for the different phases. There's different color keys that are used. And for the ferritic grains, these larger ones at the bottoms, these form what these are called packets. And this just comes from the transformation from austenite to ferrite, where these patterns in here form a preferred orientation relationship in these packets. And so this is another application question that has been around for EBSD for a long time of measuring the prior austenite grain size. And I mean, I remember, it was one of my first years, I was looking at tool steels, looking at these pictures saying, we can visually see these, how can we extract the prior austenite grain size? And I've had lots of customers want to do this. We've looked at lots of samples of trying to do it. A number of people have tried different algorithms. And so just recently, we've made some work on our side to implementing some of the algorithms that are out there to provide a solution within OM analysis. But essentially, what's happening is we start with our austenitic FCC phase at higher temperatures there on the left, and as it transforms through the transition temperature, there are different possible orientation relationships between the FCC austenite and the BCC ferrite. So it can transform by certain rules and rules with tolerances. But if we know those and we put those into the software and we do some permutations, we can reconstruct the microstructure. And that's kind of an example here going from the as-scan microstructure to the reconstruction microstructure on the right. This is for a prior austenite grain size, so it's useful for steels. It's also been used for titanium alloys in 3D printing, where that's another important feature. I'm not going to go into this in a lot of detail. There's an archived webinar from Stuart Wright at edax.com where he covers this in a lot more detail about what's going on. But I include it just because it's a question that at least we have a function in the software now to say, give it a try. And there's a lot of subtleties that go on there, but it's a step in a good direction. That comes back to this, as we do this transformation, you can also have what's retained austenite, that not all the austenite's transformed. Retained austenite can be an important factor in determining the strength, toughness, and hardness of some alloys. And so as we go to look for this, I've sometimes called it a needle in the haystack problem. We want to look at a large area, but we want to look at a fine step size. And that's where some of these faster, velocity CMOS type cameras are really useful. We can look at larger areas with finer step sizes. So that's what we're showing here, doing 125 nanometer steps, looking at the ferrite and austenite. And the blue are the smaller regions of austenite that are present. And what's kind of cool about this is that as we look at this in terms of an orientation map of just the austenite, you know, you can kind of see the colors, and the black makes it a little hard to see, but you see, you know, sort of the shadow or the outline of the parent grain orientation. So this has been used to look at some of the reconstruction as well, to show how it's working and when it's working. So we can measure retained austenite with EBSD. And of course, as we go to finer and finer step sizes, we can resolve more and more of those grains. So it starts to become a sampling statistic, sort of an approach of how to best do that. And of course, through all this, you know, one of the things we can do is in situ type of an analysis of this. So this is an example. This is work by Suzuki-san over in Japan, where he's done heating of a steel through the transition temperature. So we start here in the red, we come up through it, it transforms into the green phase, and then as we go back down, it comes back to the red phase. And so we can control, you know, temperatures going up to the 1,000 degrees C range to be able to observe these transformations in situ. And we can also do in situ deformation analysis. So this is just an example of using a stage where when we start to yield the material is sort of our 0 point. You can see the little notches where we stop the deformation and measure the microstructure at each point. And we can see with the amount of deformation how the microstructure evolves as a function of deformation. If we look at the orientation map, you know, you'd be hard-pressed to say you see a huge change in these particular maps. If we look at it with our CAM or kernel average misorientation map, we start to see it a little bit, and that top line shows our first order kernel. The bottom line shows the fifth order. So we're stepping out further. And so, you know, when we're looking at these step point-to-point misorientations, it can be very dependent on step size and the size of the misorientation gradient. Again, if our step size measures at things with a finer precision than we can measure, we'll see a little bit more blue. So that's why we can expand the size of these kernels to see more clearly the orientations or the misorientations. And then we could use something like our G-rod maps to show a grain-based measurement. So we see how that particular grain we're focused in on sort of bends and evolves as a function of strain through there. So with that, I'd first just like to say thank you. Again, it's a wide range of things we can use EBSD for on different steel applications. You know, EBSD is really an ideal tool for characterizing a lot of these different microstructural features, the grain boundaries, the phases, the local misorientations, the orientation, and the software OIM analysis. There's a lot of tools built into there for, you know, we can create a first level map, we can do interactive analysis, we can do partitioning, we can do texture analysis. That really allows us to look at these in different ways and extract out information that's important, really can help drive the continued development of these advanced steel alloys. So with that, I will stop reading and I'm going to transition over to some questions. There are a number of them there. So there's a first question that says, can you differentiate martensite and ferrite as nicely with XRD? I will say you can differentiate them, you know, as an average, but you can't necessarily spatially see the locations with XRD. XRD doesn't have the spatially specific information. And, you know, there's a number of different techniques. There's a paper that was written probably 10 years ago comparing, you know, all of these have error bars on their measurement. The thing with EBSD to remember is we're a surface measurement thing. So when we prepare a surface, we're looking at a free surface, and that can also cause some possible relaxation and transformation, whereas XRD will look at a volume. So, you know, when you're comparing measurements from different techniques, it's important to kind of know how they work and how they sample and what the effects can be, because you very rarely we'll get a perfect one-to-one comparison. We did a lot of work looking at retained austenite, both from true retained austenite versus sort of synthetic retained austenite where it was pressed together, wasn't transformed as sort of phase analysis, and trying to understand where some of these variants can come from, both with EBSD and other techniques. And so here's a question, or without EDS only, will EBSD indexing be correct? That all just depends on the phases you're looking at. So if we're, like, for example, if I'm looking at just FCC and BCC, a ferritic austenitic steel, EBSD does great with that. Or some of the carbides, the sigma phase, which is different, will differentiate those, no problem. It's when the crystallography starts to be really similar, then EDS is helpful. And then when they're similar both chemically and crystallographically, that's the martensite, you know, they're both similar in both regards, then we have to use a third approach to try to differentiate those. There's a question, can you plot the ODS in Euler space? Yes, you can. I just didn't show that. We have some talks on texture analysis on the website that go into that in more detail, but yeah, you can represent the ODS in a number of different frames. It says, here's a question, are there some measures to improve the image quality of the deformed sample in EBSD? Yes, there are. Defining improves a little tricky. You know, for all cases, you know, sample prep is really important. You want to at least make sure what you're measuring is as representative of the true sample as possible. So the best sample preparation will help improve your image quality, and that will, you know, then any decrease in image quality corresponds to the true microstructure. You know, if you have a deformed material, your image quality will be less than if you had a recrystallized material, and you want to be able to tell that. Now, you know, we're always a little careful of saying, you know, is an image quality value a definitive number? Can you compare one sample at, say, an image quality of 100 to another sample at image quality of 100? Generally, we say be very careful of that because there's a lot of factors that can affect image quality. And we published a paper about this about 15 years ago, because it can depend on your beam current, your camera settings, your sample preparation. So oftentimes we look at image quality relative within a map. People have done some work of trying to standardize that and normalize that, and I've seen stuff to say, yeah, I believe it, but you know, you're looking at a subset to say how. I've also had things where if I look at a sample, I vent the chamber and I repolish it or I rescan it without doing anything else, my image quality can vary just from that cycle. So you have to control your variables pretty carefully. There's a couple of things here that are both questions essentially talking about the spatial resolution, one in terms of retained austenite and one in terms of carbide in the nanometer range. I mean, nanometer range starts to get small for regular EBSD. You know, the spatial resolution is probably somewhere between 20 to 50 nanometers as a ballpark. And, you know, and it's very difficult to describe that because it will change both on the, you know, the atomic number of what you're looking at. The heavier it is, the better it scatters, the better spatial resolution. And it also will depend on the acceleration voltage you're looking at. I mentioned the iron carbides going, you know, MPI over in Germany, Stefan Zeffer and his group showed, you know, they could go to lower voltages, you know, say 20 to 10 or 12, and could resolve more of the carbides at finer phases. And of course, also realize that at 70 degrees tilt, you know, we do have a projection of the interaction volume along one direction of the sample. So your spatial resolution is not necessarily uniform, you know, both along the direction and against the direction of tilt. And so sometimes you have to take that into account as well. So there's a question here. It says, I had problems detecting retained austenite, and we tried transmission EBSD or TKD, which yields much better results. Yeah, and I had mentioned transmission EBSD. that's an approach where we use a thin foil and we look at the sample in reflection, in transmission rather than reflection. Because of that, our interaction volume is minimized and we can get much better spatial resolution. Which, yeah, exactly. You can certainly improve spatial resolution and get better resolution that way. There's a question that says on slide 49, is EDS mapping superimposed on the image quality map? I'm going to go to that slide to try to answer that. I'm guessing the answer is going to be yes. Yes, in both cases, those are superimposed, just to provide some level of grain contrast. One of my friends from Japan, Yoda-san, very nice to have you on and have a question from you. Hello. Do you have any problems getting a large area montage? And I heard it is difficult to measure a large area montage with the OMDC. In general, I would say no, there are not problems. You know, you're always trying to fit together the sections, and it depends on the seaming of the detector. So, I mean, the biggest problems you can have with montage, the two that come to mind, you know, first, you ideally want the top and bottom of the sample to be planar. You don't want a sample that's off, because we're trying to move the stage to keep the sample in focus, and the more that plane isn't flat, the more corrections we have to make, and the more corrections you have to make, the harder it is to get the corrections right. The other thing that's tricky is making sure that your system and your microscope are paired together in terms of how they're measuring distance. Because, you know, we tell them the microscope stage we are moving 100 microns. And if we think it's moving 100 microns and the stage thinks it's moving 100, but the image thinks it's moving 98, there's, you know, 2 microns difference. And if you're looking at, you know, 2 or 5 micron step sizes, that's generally not a problem. But if you're looking at a scale where you can see, sometimes you'll see that the matchup between the seams of those different tiles is not perfect. And so, you know, we have some functionality in OIM analysis that allows us to play with that a little bit more, but of course it's more time consuming than just an automated analysis. And so the other comment, of course, OIM data collection is an older legacy product. You know, our current version of Apex has some newer things implemented to try to help with that. Certainly a lot of the issue with larger areas is managing the memory of the system. OMDC was a 32-bit application. Our latest team is 64-bit. So it can handle larger amounts of data to try to facilitate that. I'm going to take one more question, and then we're kind of at the time limit. Other questions that are submitted, we will address separately by email. The final one I'll take just kind of goes back to which polishing method do you use to get this data. I'd say most of these, or probably all of these, were collected with samples that were mechanically polished and down to colloidal silica, either a 0.02 or a 0.05 final polish slurry. And if you're interested more on that, we have saved webinars specifically for sample prep. We are starting to do more ion beam preparation to experiment that, particularly for retained austenite, to see if that has an effect on that, but that's just work that's starting. So with that, I'd like to thank everyone for your attention. I'd like to say thank you for submitting questions, and again invite you to tune in next month for Dave Roanhorst's talk on 3D microstructures of additively manufactured materials. Thank you very much.